Hi students, welcome to Max Point of View. Today we are going to understand the concept of electromagnetic induction and its application to AC generator and transformer. This is part C of electromagnetism. So this chapter has concept as well as theory solution as well as numericals. All these videos are available in the description box. So whenever it comes to electromagnetism, many students will think this is a tough chapter. No, it's not like that. Any question related to electromagnetism you can solve within 1 minute, that too for 3 to 4 marks. So understand the concept. If you understand the concept, everything is easy. Within 1 minute you can get 3 to 4 marks. So without wasting any time, we'll start with the concept. Party of electromagnetism, Hans Oersted taught us we can produce magnetic field around a conductor, correct? Whenever a current carrying conductor is there, there will be a magnetic field around it. This is what found by Hans Oersted. But do you think, can we generate electric current because of magnet? Only just because of magnet can we generate electricity? The answer is yes. This is what found by Michael Faraday. Michael Faraday has done many number of experiments and trial and error method to found electricity just because of magnetic field. So before understanding the concept, there is a name for that concept also. Before going into the topic, we need to understand few terms. Okay, these are the terms are going to confuse the students. So if we understand all these things, even though you know the concept, you don't have to by heart it. Now listen, magnetic field and magnetic flux. So first we'll understand what is magnetic field. Many students know this one. We know all the field lines, okay, originate from north to south. They'll move from north to south outside a magnet. Inside a magnet, it is from south to north, correct? So these are called, so all these lines are called field lines. Okay, those are called magnetic field lines or magnetic field. Togetherly, all the complete magnetic field togetherly called as magnetic flux. Okay, so this is how you need to understand whatever the words you are going to learn from the textbook. Understand the meaning of it, then you will understand the concept clearly, or else few words you will keep on using it and you don't know the meaning. What do you mean by magnetic flux? Togetherly, all the complete field lines, magnetic field lines are called magnetic flux. So magnetic field, those are the lines. Togetherly, magnetic field lines are called as magnetic flux. That's it. Then EMF, electromotive force. See, when it comes to EMF is nothing but voltage. Keep this in mind. EMF is nothing but voltage. So whenever we talk about this concept, sometimes they use EMF or sometimes they use current. So whenever there is a current, okay, whenever there is a current, assume there is a EMF. Okay, assume there is an EMF. So if current is there, voltage will also be there. If they are talking about EMF, okay, if they are talking about EMF will be generated or EMF will be induced. Okay, induced, I am going to tell you what is the meaning of it. Okay, EMF will be induced or the EMF will be produced, all those things. That means current is also produced. So what you have to think, if EMF is there, current is there. What is EMF? EMF is nothing but voltage. If voltage is there, current is there. If current is there, voltage is there. This is what we have to assume, because sometimes they tell us EMF is induced, sometimes they use current is induced, both are same. Okay, the EMF is different, current is different, but the meaning, whatever we are going to learn here, okay, if EMF is generated or induced, current is induced. That is what the assumption we have to make. Next, induced. The word induced means generated or produced. Okay, induced EMF, generated EMF. So I told you, because of the magnet we are going to produce the current, correct? So instead of using the word produced, we are going to use the word induced, because that is what mentioned. This is the keyword. Okay, so whenever there is a magnet, EMF will be induced or current will be induced. So that is our aim. Now we'll talk about the name of this process. The name of this process, because of the magnet we are going to produce electricity, correct? There is a name for it. That is nothing but EMI, electromagnetic induction. Electromagnetic induction. So how to define this one? whenever there is a change in magnetic field lines. Okay, whenever there is a change in magnetic field lines, an EMF will be induced between the ends of the conductor. Okay, see, I'll repeat one more time. Whenever there is a change in magnetic field lines, okay, whenever only there is change in magnetic field lines, then EMF will be induced between the ends of the conductor as long as there is a change in magnetic field lines. So current will be induced or EMF will be induced only when there is a change in magnetic field lines. So what do you mean by changing magnetic field lines? So sometimes they'll use magnetic field lines. Okay, sometimes they'll use magnetic flux. You know, the complete magnetic field lines are considered as magnetic flux. You need to understand like this. Okay, so how to define it in a different way? Whenever there is a change in magnetic flux, change in magnetic flux is nothing but change in magnetic field, correct? So whenever there is a change in magnetic flux, an EMF will be induced, a current will be induced. You can write it as EMF will be induced or current will be induced as long as there is a change in magnetic field lines or as long as there is change in magnetic flux. So if there is a change in magnetic flux, okay, number of field lines are varying, increasing or decreasing, only then current or EMF will be produced. If the number of field lines are same, okay, it's not changing, then no EMF will be generated or induced. So whether they are going to, how they are going to change and how they are going to not change, being exactly the same numbers, all those things we are going to learn here in this experiment. Now we'll jump into the topic. Now listen. So north, south, you can choose. See, sometimes we are going to use north and south, and sometimes we are going to use south and north. Okay, any direction, you need to understand everything. Okay, so there is no fixed rule that I have to always write north here and south here. Okay, magnetic polarity can be changed. So what happens, all those things, if we change all those things, we are going to learn here. Now listen. See, first, whenever these kind of diagrams are come, first we need to understand what are there. So this rod, this rectangular shape is a wooden rod or paper. Okay, wooden rod or paper coil or wooden coil. Okay, on that we have a copper wire. It is connected to galvanometer. So what is the function of galvanometer? There are two functions. One, it is to find the weak current in the circuit. Second one, to find the direction of current. So in this experiment, we are going to use the galvanometer to find the direction of current. That's it. Not to find the weak current. It is to, now in this experiment, we are going to use the galvanometer to find the direction of current. So this setup we understood, and there is a magnet. Now listen. So whenever I move this magnet, okay, magnetic field lines keep on changing. So whenever I move, whether towards or away from it, okay, towards or away, okay, magnetic field lines will keep on changing. If magnetic field lines are keep on changing, magnetic field lines are called magnetic flux. If the magnetic flux is changing, then current will be induced or EMF will be induced in the coil. If it is stationary, if the magnet and as well as the solenoid both are stationary, then no EMF or no current will be induced in the circuit. Okay, it has to keep on moving, to move towards it or away from it. In any one direction it has to move. If it is not moving, no current will be induced. And I told you what is the function of galvanometer, to find the direction of current. If the current is not produced or induced, what will be the direction? Direction will be just towards up, zero. Okay, no direction, no towards left, no moving towards left or no moving towards right. It will be like this. Okay, upside. That's it. Next, if I move this magnet, okay, the same north pole on the left hand side and south pole is on the right hand side. Now I am trying to move this one. Okay, whenever I try to move this magnet, okay, north side is on the left hand side and south side is on the right hand side. This is very much important. This direction is also very much important. Listen, whenever which side of the pole is moving towards it, which side of the magnet is moving towards the coil? North side. So this side becomes north and this side becomes south. Okay, this, see which side is moving towards it. See, whenever the magnet is moving towards the solenoid, this is nothing but solenoid, right? So whenever this magnet is moving towards the solenoid, which pole is near to this one? north, right? So this also, okay, on this side of the solenoid also becomes north. Keep that in mind. If south is moving towards it, this becomes south. Now anyhow north is moving, so this becomes north. And one thing you need to understand, current always flows towards north, always flows towards north. Current always flows from south to north. Keep this in mind, or you can remember it as current always flows towards north. So whatever the question, these are the possible diagrams. Okay, so here if you understand all the complete concept, then whatever the question they ask, you can easily answer. You will understand all these things in the theory solution which is there in the description box. Now listen, whenever the magnet flow move towards it, the same pole, whatever the pole is near to the solenoid, that the same pole will be occurred here. Okay, this one solenoid becomes north side and this side will be south, and current always flows towards north pole. So towards, this is north pole, current is flowing from the south to north. This is important direction of current. So for every diagram, okay, first we are going to identify north and south pole, then the direction of galvanometer. Now see the direction of current is moving towards right. So the direction of galvanometer will be towards right. So in exam or in any one of the questions, they are going to ask in which direction current is flowing. Whether assume this is A, B, A, B, A, B, A, B. Whatever the letters they are talking about, you need to understand the concept. So in this case, okay, in this case, current is flowing from A to B. Okay, so it is A to B towards right. The direction of galvanometer is A to B, correct? It is from A to B. In textbook they may use B here, A here. Don't get confused. You need to understand, first understand the concept. Based on that you write the value. So in the questions they are going to ask whether it is from A to B or B to A. In this question, okay, in this concept here it is from A to B. Okay, next, see, now we'll understand the same topic. Okay, now anyhow we have moved this magnet towards it slowly, but what happens if we move it rapidly? If we move it rapidly, so that means what happens here, whenever we are moving, okay, towards it, magnetic field lines keeps on increasing. Whenever you are moving it towards it, magnetic field lines keeps on increasing. That is nothing but a change. That's why current will be produced. If you move it fastly, rapidly, the magnetic field lines remain same, moving towards it. But what about the speed? Speed increases. So it depends upon many things. How much current is produced, that depends upon, okay, the number of turns of the coil, the number of turns. If the number of turns are more, current produced will be more. Okay, if the number of turns are more, current produced will be more. Then if we use, instead of this magnet, if we use much stronger magnet, again the current produced will be more. Then what is the one condition? If it move fastly, okay, if it move rapidly, the deflection, so the current produced will also be more. More the speed, more the current. Stronger the magnet, more the current. More the number of turns, more the current. All these are the three factors to increase the magnitude of current in this electromagnetic induction process. Understood? So now if you move fastly, the direction remains same. The direction will be towards right only, but the current, more current will be produced. Now we'll go for the different question. Now anyhow we have moved this magnet towards it, and if assume the magnet is somewhere here, somewhere too close to the circuit, and the magnet is not moving, it is stationary, then what is the condition? Only if it moves, there will be a change in flux. Okay, what is the definition of EMF? As long as there is a change in flux, EMF will be induced. If there is no change in flux, if the magnet is not moving, that means no change in flux, so no EMF will be induced. If you keep the magnet somewhere here, and if the magnet is stationary, if the magnet is not moving, that means no EMF will be induced. Keep this in mind. Now the same magnet, instead of moving towards, it is moving away. Whenever it is moving away, the magnetic field lines will keep on decreasing. If it is moving towards, okay, magnetic field lines will keep on increasing. If it is moving away, magnetic field lines will keep on decreasing. See, all these points, whenever you are understanding through the video, make a note of it. then it will be very helpful during the next time whenever you are studying, and these will be the key points. Okay, next, whenever it is moving away, okay, this becomes south. Even though the closest pole is north, okay, this becomes south. So why? Because whenever it is moving towards it, the same pole, whatever the pole near to it, we get the same pole. But whenever it is moving away, the opposite poles, okay, will get the opposite pole, which is the near pole north of the magnet, so it becomes south. If this is south, this becomes north. So for every direction, north and south pole, we have to mark. Then direction of current, whether it is from A to B and towards right or towards left. In some question, they will ask whether it is towards left or towards right, or whether they ask A to B or B to A. You have to be ready with everything. Okay, now we know current always flows towards north, correct? So towards north from south, so it is from B to A, so it is towards left. So in this concept, it is from B to A and it is towards left. Okay, towards left. Now what if we change the direction of magnet? What if we change the magnet? Initially, whenever we are moving towards it, we had north and south, correct? So what if the same concept, moving towards it, but here we have south and north, okay, and south pole is near to the solenoid. Now what happens? Whatever the polarity we have, whenever we are moving towards the same pole. See here, moving away, that's why we had a different pole. Whenever you are moving towards it, we'll get the same pole. See, moving towards it, we got the same pole. Here also we are moving towards, correct? So this, so whatever the south pole we have, the same pole we get here, and this side will be north. And we know current always flows towards north from south. Always current flows from south to north. So in this diagram, okay, D, what is the direction of current? It is again B to A towards left. Okay, now all these things, in all the cases, we were moving the magnet, correct? We were moving the magnet and the solenoid was stationary. What if we make this magnet, okay, magnet stationary, will move the solenoid? Whatever we move, okay, if we move the solenoid or move the magnet, the results will be same. Assume in this case the magnet is stationary, the solenoid is moving towards it, the same thing. North pole we will get it here, and south pole, and we know current always towards north. So keep this in mind, whether we are moving magnet or a solenoid, we'll get the same results. Okay, so after learning all these things, we are going to learn some conclusions. Whatever the concept we have learned, based on that we'll conclude it. Now current will be induced or EMF will be induced, any one we can use. Current will be induced or EMF will be induced only when there is a movement in the solenoid or magnet. Okay, either magnet has to move towards the solenoid or solenoid has to move towards the magnet. If both of them are stationary, then no EMF or no current will be induced. Keep this in mind. Next, we'll talk about direction of current. Direction of current depends upon whether the magnet is moving towards it or away from it. As the motion of the conductor changes, okay, as the motion of the conductor changes, okay, like this or like this, the direction of current also changes. If it is moving towards it, the direction of current will be in one direction, whether sometimes it may be anti-clockwise or clockwise. If it is moving away from it, it will be exactly to the first case. Then the current can be increased. What are the factors which affects the current in the solenoid in induction, electromagnetic induction? First thing, the speed of motion of magnet or solenoid. Okay, if the speed is increased, current is increased. So these two are directly proportional. So if you want to increase the current in the solenoid, we have to increase the speed. A rapid movement, okay, the direction remains same, but whenever there is a rapid movement of magnet towards the solenoid, okay, then more current will be produced. Then number of turns of the coil, number of turns, more the number of turns, more current will be produced. Okay, next, the thickness of the coil or area of cross section. So the thickness of the coil, okay, the wounded around it, right, the coil which is wounded around the paper or a wooden piece. Okay, the thickness, if the thickness is more current will be produced. Then the last one, instead of using a normal magnet, if we use a stronger magnet, more current will be produced. So these are the concluding points. If you understand the complete concept, whatever the question they ask, we can easily answer any question. So when it comes to electromagnetic induction, okay, what is the energy transformation in this case? See, because of the movement in the magnet, whether it is towards or away from it, current is produced. What is produced? Current is produced. So that current is nothing but output. What is the input? Okay, what do you mean by energy transformation? Energy transformation is we give input and the output will be produced, correct? So what is the input we are giving? Movement is nothing but mechanical energy. Movement is nothing but kinetic energy, but we don't have to go specifically. Kinetic energy is nothing but the part of mechanical energy. So movement, whenever because of the movement current is produced, so input is mechanical energy, output is electrical energy. So energy transformation is mechanical energy to electrical energy. So in this case, okay, in electromagnetic induction, what is the source which producing the electric current? Mechanical energy. This is the source. Keep this in mind. So when it comes to electromagnetic induction, we produce the electricity using a magnet. If assume there is no magnet, if we don't want to use magnet, then we can use a circuit to produce the same induced EMF or induced current here. So here a coil. So this is nothing but coil S. Okay, it is nothing but just a coil which is connected to the galvanometer. Nothing, no battery, nothing. Just a coil is connected to the galvanometer. And there is one more coil which is called as P. Here it is connected to battery and a rheostat. So here the important thing is rheostat. Okay, what do you mean by rheostat? It is a variable resistor, so we can keep on changing the values of the resistance, correct? There will be a knob. A rheostat will be this big, okay, device. On that there will be a knob. We have to keep on moving the knob to increase or decrease the resistance. If the resistance is varied, current in the circuit will also be varied. So here whenever there is no dot, whenever there is no dot, it is a open circuit, current will not flow. So whenever there is a dot, that means there is a connection. This is a closed circuit, so current starts flowing. Whenever the current starts flowing, okay, here this current will produce a magnetic field around it, correct? Because of that magnet, there will be a current will be induced. We know because there is a movement in the magnet, okay, motion in the magnet, current will be induced, correct? That is nothing but induced EMF or induced current. But here in this case we are not using actual magnet, we are using a circuit. Here anyhow the current flows, the magnetic field will be produced around it. Because of that magnetic field, okay, there will be a induced current here. Okay, now assume we are giving a 5 amperes of current. Now do you think the current will be induced here? No. Why? Because what type of current we are giving? Okay, DC current. What do you mean by DC? We have a constant magnitude. When it comes to DC currents, it has a constant magnitude. That means the value of current will not be changed. So if the value is not changed, if the magnetic field, whatever for 5 amperes, we'll get a constant magnetic field, correct? If what is the main thing about electromagnetic induction? There should be change in magnetic flux. Well, you know what is magnetic flux? Magnetic field lines should keep on changing. So here, as we are giving 5 amperes of current, any ampere, you can take any value of current. If the current is constant, magnetic field will also be constant, correct? There is no change in magnetic field, so no EMF or no current will be induced in the coil S. Okay, now using the rheostat, if you change the value of resistance, what happens? Now assume we are increasing it. Assume we are increasing the value of current, that means we are reducing the value of resistance. So using the rheostat, if we reduce the value of resistance, current will be increased in the circuit. So when the current increases, the direction of galvanometer changes. If you increase the value of current, okay, assume the direction of galvanometer is towards up. If you decrease the value of current, the direction of galvanometer will be exactly opposite. But if you just increase it and leave it, so again there will be again we are going to give a fixed value of current, so fixed value of magnetic field, so there is no change in magnetic flux, no current or EMF will be induced. So what is the important thing? You have to keep on changing the value of resistance based on the resistance value. If you keep on increasing the value of current, then the direction of galvanometer will be in one direction. If you start decreasing it, the direction of galvanometer also changes. Then see, important thing in this circuit here, this coil P acts as a magnet. Coil P acts as a magnet. This is a normal solenoid. Okay. Next, as there is a change in magnetic flux, see, this is the symbol for magnetic flux. Keep this in mind. Okay. Change in magnetic flux will induce the EMF. If the magnetic field lines, if we are giving constant value of current, same constant magnetic field will be there, so no EMF will be induced. Then direction of G, so assume it is upward, okay, for increasing the current in the circuit, okay, then direction will be upside. If you decrease the value of current, direction of galvanometer will be exactly opposite. Then this acts as a primary side. Primary means always in initial point. Because of this is producing, right? So this is primary and this will be secondary. Then where we are using this principle? This principle used in transformers, which we are going to learn at the end. Now we'll talk about Faraday's laws of electromagnetic induction. There are two laws. First thing, whenever there is a change in magnetic flux linked with a coil, an EMF will be induced. This will be as long as there is a change in magnetic flux. This is what we have learnt in electromagnetic induction. The second law, the induced EMF is directly proportional to the rate of change of magnetic flux. So that means how much there is a difference. Rate of change of means how much there is a difference, right? More the difference, more will be the induced EMF. And this, if the rate of magnetic flux is changing with a constant rate, okay, constant rate, assume 0 to 5, 5 to 0, the value, okay, initially the magnetic field lines were, flux was 0, now it is 5, then it is 0, then it is 5, again, whenever there is a change in constant magnetic flux, a steady current will be induced in the coil. So these are the two laws. Now we'll talk about the factors which affect the induced EMF. Factors which affect induced EMF. The first one, okay, that is the first we'll write the formula. Okay, first we'll write the formula. Based on it, we can easily write the factors. So induced EMF is equal to, this is the formula, N into delta flux by delta T. Okay, listen, see, delta, okay, delta is nothing but now you can assume it as triangle. Triangle represents there is a change in the value. This is nothing but magnetic flux, correct? Magnetic flux symbol. Okay, so a circle and a straight cross line, okay, dividing the circle into two parts. Okay, this is nothing but the symbol of magnetic flux. Okay, the triangle means there is a change in the flux value. Only when there is a change in flux value, we'll get the induced EMF, correct? Then delta T means as the flux changes, that will take some time to change, right? Because of that, so there is a change in time. Then N represents number of turns of the coil. So what are the factors affecting induced EMF? Number of turns of the coil, rate of change of magnetic flux. So what do you mean by rate of change of? That means whatever the value we are going to talk about divided by time. Rate of change of magnetic flux. Rate of change of magnetic flux. So magnetic flux divided by T, that is nothing but rate of change of magnetic flux. So this is the Faraday's law and these are the two factors. Now we'll understand how to find the direction of induced EMF. So we know the EMF will be induced as long as there is a change in magnetic flux. So whatever the induced EMF is there, we need to find the direction. How to find that? There are two rules. First, the rule is Lenz's law. Lenz's law or Fleming's right hand rule, any one we can use to find the direction of induced EMF. So here first we'll understand some basics about it, how to find it. Listen, we know whenever there is a magnet, north pole and south pole, we know magnetic field lines outside the magnet will move from north, correct? Outside the magnet it moves from north. So the same field lines will come here and go inside the south, correct? See, from for normal magnet, from magnetic field lines will move from north to south outside. Inside it is from south to north. This we should know. This is the basics of magnetism. Now we'll talk about how to find the what exactly is Lenz's law. So according to Lenz's law, the direction of induced EMF will be opposite to the cause producing it. It always opposes the cause producing it. So here, what is the cause producing it? The cause is this magnet. Because of this magnet, okay, EMF will be induced. So the direction of induced EMF will be opposite or opposes the cause producing it. This is the cause. Because of the magnet, the EMF will be producing. So always the direction of induced EMF will be opposite to the movement of this magnet. How is that? That is what we are going to understand here. Now listen. So this is what electromagnetic induction experiment we learned, okay, in the beginning, correct? So whenever this magnet is moved, okay, the same side will get here, correct? This is what we have learnt. So this side will be opposite, and we know when it becomes a magnet, the magnetic field lines will be from towards, see, the magnetic field lines will be from the north, it will go outside. So the magnetic field will be outside like this, and because of this magnet also, so it also is flows from north. So it is exactly opposite. So this is the direction of induced EMF. So now the same thing we apply it here. Now whenever the same magnet is moving away, this becomes south and this becomes north. This becomes south, this becomes north. Whenever it is a south pole, so magnetic field lines will be towards it. Magnetic field lines will be towards it, and here it is away, correct? See, because it is moving away, the magnet is moving away. Here the magnet was moving towards it, here the magnet is moving away, so it is going away. See, these two are opposite. This is nothing but Lenz's law. So Lenz's law states that the direction of induced EMF will opposes the cause producing it. Just now we have learnt Lenz law. We need to learn how this Lenz law is based on conservation of energy. What do you mean by conservation of energy? One form of energy is completely converted into another form of energy when we assume there is no loss of energy. When there is no loss of energy, the complete energy will be converted into other form. So when it comes to Lenz's law is based on what? Whenever the magnet is moved towards the solenoid, a current will be produced, correct? So here what we are giving input, that is nothing but movement of magnet. Movement of magnet is nothing but mechanical energy. So mechanical energy is spent in order to produce electrical energy. So whatever the mechanical energy is there, okay, that is converted into electrical energy. So one form of energy is converted into another form, so the total energy remains constant. This is nothing but conservation of energy. So in Lenz's law, so the complete mechanical energy is converted into electrical energy. So Lenz's law is also based on the conservation of energy. Now we'll talk about Fleming's right hand rule. First we'll understand how to define it. Stretch your, this is how you are going to write it in the exam. Stretch your thumb, forefinger and middle finger of your right hand and hold it like they are mutually perpendicular to each other. See, this thumb is perpendicular to the forefinger and the forefinger is perpendicular to the middle finger. Now we'll assign what are these fingers represents. The thumb indicates the direction of motion of conductor, that is nothing but force. Okay, force. Then the forefinger represents the direction of magnetic field, the direction of magnet or magnetic field. The middle finger represents the direction of induced current or induced EMF. This is very important. So whenever we are using right hand, Fleming's right hand rule, we are going to find what? The direction of induced EMF. That is the aim of using Fleming's right hand rule. Okay, why we are using Fleming's left hand rule? To find the direction of force, induced force. So in whenever the force is created, okay, so whenever there is an electric field and magnetic field, a force will be generated. So what is generating here? force. The direction of force we are going to find using Fleming's left hand. When it comes to Fleming's right hand, in this case, what is generating the induced EMF or induced current? Whatever it is generating, the direction of induced EMF or induced current we are going to find using Fleming's right hand. So when it comes to application of Fleming's right hand rule and left hand rule is rarely asked, very rare. But when it comes to Fleming's left hand rule, it is very important. This is what we have learnt in part B of this electromagnetism. In part B, we have learnt how to use this Fleming's left hand rule. Okay, so very important is how to use the Fleming's left hand rule. Learn it, that is compulsory. Now we'll talk about AC generator. So first we'll understand the definition of AC generator. AC generator is a device which converts mechanical energy into electrical energy and which works on the principle of electromagnetic induction. So what is electromagnetic induction? That is what we have learned in the beginning of this chapter. Now listen. So when it comes to AC generator, the important things are diagram and principle. Diagram is there. AC generator and DC motor diagram can be asked for 3 to 4 marks. Okay. And the principle. What is the principle of AC generator? It works on the principle of electromagnetic induction. Then parts and their functions. So when it comes to DC motor and AC generator, the parts remain same. Parts remain same except only one part. Here see the slip ring commutator. Slip ring commutator in DC motor, it was split ring. The ring was split into two, correct, in DC motor, but here the complete ring is there. So here the difference is the slip ring in DC motor, it is split ring. Then working is not there. And differences we are going to learn. Differences between AC generator and DC motor, and frequency of alternating current. This is not there in the syllabus. Frequency of alternating current, the formulas, all those things, nothing is there. Okay, frequency in household, this is there. Very simple answer. What frequency we are using in our household circuits? That is nothing but 50 Hertz. This was asked in 2025, a question in the annual exam for 1 mark. So how easy is that? What is the frequency used in household circuits or throughout India? See, throughout India, what is the frequency? 50 Hertz. It will never change. Keep this in mind. When it comes to frequency of light, okay, in the light chapter, frequency and frequency in electricity, magnetism, all everywhere, the frequency remains unchanged. It remains same. Keep this in mind. It is always 50 Hertz in electromagnetism and electricity, but there is no fixed frequency for light. Keep this in mind. So here we are not going to learn how to draw the diagram. That you can aramse learn. Okay, just practice it. Okay, the parts and their functions remain same compared to the DC motor. The same parts we are using. The only change is here in the DC motor we used to get the current from the battery, but here we are going to generate the current and giving it to the load. That's it. Now we'll talk about the differences between AC current and DC current. So we know there are two types of current, correct? So when it comes to AC and DC, we need to understand the differences also. So first, when it comes to DC, it has a constant magnitude. Constant magnitude. What do you mean by magnitude? Magnitude is nothing but the value. DC is nothing but it has a constant value, but when it comes to AC, it has a varying magnitude. Then DC current always flows in one direction. Okay, so you have to write, okay, in a sentence when you are writing differences. Okay, but you should not write like this. You have to write it in the form of sentence. See here something incomplete, right? You have to complete it. It has a constant magnitude, it has a varying magnitude. Flows in one direction. Flows in one direction. AC we can write it as flows in bidirection, in both the direction, or you can write it as it reverses its direction periodically. It reverses its direction. Okay, reverses its direction periodically. Then it is obtained from a cell, or battery. Okay, It is obtained from AC generator and mains. So these are the key differences between AC and DC current. Now we'll talk about advantages of AC current over DC current. So the first point, it is very easy. See, it is cheap and easy to produce. AC currents are cheap. Okay, cheap means affordable and easy to produce. Then efficiency of AC current is more than the efficiency of DC current. The third point, if we want to convert the AC current into DC current, this is a very easy process. Okay, next, whenever we want to change the value of AC voltages, okay, AC voltages, that is nothing but increasing the value or decreasing the value. Okay, we can do it in AC, but in DC we cannot increase or decrease. Okay, for increasing we use it as step up. Step up means increasing the voltage, step down means decreasing the voltage. This can be done only in AC. It cannot be done using DC. Why? Because DC produces constant magnitude. If you want to step up or step down, increase or decrease, we should not have the constant value. It should be keep on changing. Okay, next, the final will be whenever we are transmitting for a longer distance, whenever we are giving the power from sending the power from one electricity from one point to the longest point, the loss of energy in the form of AC is much less compared to DC. In DC, the loss of energy in the form of heat is more. These are the advantages of AC over DC. Now we learn the differences between AC generator and DC motor. First, so we'll go for AC generator. In AC generator, we convert mechanical energy into electrical energy. But when it comes to DC motor, we convert electrical energy into mechanical energy. This is the first simple difference. Then we'll talk about the principle. So AC generator works on the principle of electromagnetic induction. The DC motor works on the principle of force on a current carrying conductor placed in a magnetic field. This is the principle of DC motor. Then when it comes to AC generator, we use Fleming's right hand rule. Fleming's right hand rule. When it comes to DC motor, we use Fleming's left hand rule. When it comes to AC generator, we are using two slip rings, separate slip rings. But when it comes to DC motor, we use two parts of a slip ring. That means in a same slip ring we divide it, okay, cut it into two different parts. That is nothing but split rings. Okay, split rings. When it comes to AC, we are using two. In DC, we are using one slip ring into two different halves. That's it. Like we have a differences between AC generator and DC motor, we have some similarities also. So what are those similarities? In both AC generator and DC motor, the armature coil, okay, armature coil rotates. Correct? In both the cases, the armature coil rotates. And the second similarity, in both the AC generator as well as the DC motor, the transformation of energy takes place. That means electrical to mechanical or mechanical to electrical. In both AC generator and DC motor, transformation of energy takes place. Now we'll talk about our final concept and a very important concept when it comes to examination, because based on the transformers, definitely one or two questions will be there. Maximum marks can be asked from a transformer is 4 marks, 4 to 5 marks. Okay, and this concept is very easy understanding concept. If you understand it, any question you can answer. There is no logical questions can be asked based on the transformer. All the questions are direct, and for that you need to have the complete knowledge. So first, definition of a transformer. Transformer is a device by which we can change the magnitude of AC EMF by increasing or decreasing. What do you mean by EMF? That is nothing but voltage. What do you mean by vary? That is nothing but changing. Correct? So we can increase the value of AC voltage or decrease the value of AC voltage. This is the definition of transformer. Then principle. What is the principle we use in transformer? Or they can ask in a different way. Based on which principle the transformer works? It works on the principle of Faraday's laws of electromagnetic induction, or you can write it as electromagnetic induction, or you can write it as mutual induction. In any one of these answers, you will get the full marks. Next, frequency. Keep this in mind. Whenever we talk about transformer, that is nothing but we can increase the value of voltage or decrease the value of voltage, but frequency remains constant. So whatever the input value we give, okay, the output value will also have the same frequency. Okay, so in India we use 50 hertz, correct? 50 hertz. Okay, but when it comes to transformers, we are not going to talk about the value. We talk about only one thing. Whenever throughout the transformer working, the frequency remains same. Keep this in mind. Next, core. So here this rectangular, okay, the rectangular 3D, correct, the 3D object in both the cases. Okay, these are the two types of transformer which I am going to explain later, but now you need to understand what is core. This rectangle, okay, is considered as the core. Okay, for core we use soft iron. We use soft iron. Keep this in mind. Okay, why we use soft iron? Because soft iron has low retentive property. What do you mean by low retentive property? This is what we are learning from part A, right? We are using core soft iron as a core. Why? Because it has low retentive property. Then primary and secondary side. See, when you take a transformer, there are two types of transformers. Don't worry about it, we are going to learn it later. Now when you take any transformer, the left side is primary, the right side is secondary. So whatever the voltage we want to change, we always give it to primary. Keep this in mind. Whenever we want to change any voltage, change means increase the value of voltage or decrease the value of voltage, we will always give it to primary. So if we want increased value or decreased value based on the type of transformers, we are going to get it at secondary. Whatever we give is always to the primary, whatever we get, that is always from secondary. Keep this in mind. Then what type of current? So when it comes to transformer, we always use AC current. Keep this in mind. We always use AC current. We cannot use DC current. Why? Because in DC, okay, first we learn why we are using AC. In AC current, we know the value, the magnitude will keep on changing, correct? So for magnetic flux, what is important? Magnetic flux. The value of current should keep on changing, then only there will be a change in magnetic flux. Because of the magnetic flux, change in magnetic flux, okay, EMF will be induced at secondary. EMF will be induced at secondary. This is nothing but electromagnetic induction. For that, value should be keep on changing. In AC current, we know the magnitudes, we have a varying magnitude. That is what we have learned in differences in AC and DC current. But when it comes to DC current, the magnitude is constant. Whatever, if I give, okay, 50 volts of DC, the value remains always 50 volts only, it will not change. That is wrong when it comes to transformer. The value has to change. When it comes to DC, the value remains constant. Because of the constant voltage, no flux will change. There will be no flux. What do you mean by flux? Magnetic flux. The magnetic field lines should keep on changing, correct? It has to increase or decrease. It should keep on changing. But when it comes to DC, the magnetic flux, okay, remains same. So no voltage will be generated or no EMF will be induced at secondary. So that's why we cannot use DC. Next, construction. When it comes to construction, that is not there in the syllabus. That is not there in the syllabus. Now when it comes to turns ratio, it is very much important, not only for the theory as well as the numericals. See, so when we talk about transformers, we are going to use some symbols like E, EP, ES, okay, NP, NS, IP, IS. See, this P represents primary side, P represents primary, S represents secondary, E represents, so this E is nothing but EMF. EMF is nothing but the voltage. So EMF or E represents voltage. So EPA means voltage at primary, voltage at primary. ES means voltage at secondary. In any one of the diagrams, voltage at secondary. Then N represents number of turns. See here, this is one turn. 2 turn, 3 turn. Okay, so based on the number of turns only on primary and secondary, okay, we have two different types of transformers. Okay, next, n represents what? Number of turns at primary. Okay, here in this case, primary number of turns are more compared to secondary, correct? Whenever you want to write a diagram of a transformer, you have to use scale and pencil. Okay, you should not write it like this. Okay, next, I we know that is current, and IP represents current at primary, current at secondary. Now we'll talk about turns ratio. So turns ratio, when it comes to transformer, there is a formula. See, the derivation of turns ratio is not there in the syllabus, so don't worry about it. Remember this formula: ES by EP is equal to NS by NP is equal to IP by IS. It is not IS by IP like this, it is IP by IS. All those differences we are going to learn later. Okay, first, for now, turns ratio formula is this one. In the numericals, how we are going to use all these things, okay, I have to explained in the numericals. In the numerical video, you will understand all these things. The numerical video is available in the description box. Next, okay, so why we require turns ratio? Why we require turns ratio? Very simple. Based on, okay, primary side. Okay, primary side, if I give you the value of primary side, okay, how much voltage we can generate at secondary side, that can be calculated using turns ratio. Or else, if I give you, if we are talking about current, if I give you this much of current, how much of current we can generate on the secondary side, or vice versa. So if I tell you the value of secondary side, we can calculate at primary side also by using turns ratio. How to use this turns ratio to calculate the values, that is there in the numericals. Now don't worry about it, just remember this value, turns ratio formula. Then compare power input and power output. One question you can expect based on this one, power input and power output of a transformer. So what is the comparison? Comparison is very simple. PI is equal to PO. Power input is equal to power output. Whenever they talk about comparison, if you want the answer in the form of ratio, it is 1:1. So this is very much important. Whenever they talk about comparison, that means you have to write the answer in terms of ratio. Power input is equal to power output in a transformer for an ideal condition. For normal condition, power input cannot be equal to power output, correct? Because some loss of energy will be there. So power input is always greater than power output. When it comes to ideal transformer, ideal means which is not practical, theoretical transformer, power input will be equal to power output. So it is 1:1. Okay, then if they talk about this one, general practical transformer, the value you cannot write it in the form of numbers, then you can write it as power input is greater than power output. 99% of the time they talk about ideal transformers only. So if they don't mention whether it is an ideal transformer or a practical transfer, you always go with the first one only. Power input is equal to power output. The value comparison is 1:1. If they mention, only if they mention practical transformers, then or actual transformers, then you have to go for this one. Okay, 90% of the time they ask questions about ideal transformers only. Practical or actual transformer, if they ask, this is the answer. Power input is always greater than the power output, because there will be a loss of energy. Why power input is equal to power output in ideal case? Because there is no loss of energy. That is the assumption. They'll ask that question also. What is the assumption made by you? That is nothing but power output is equal to power output. That is comparison. Assumption is no loss of energy. When it comes to actual or practical transformers, power input is greater than the power output because there is a loss of energy. That's it. Now we learn the important topic about transformers. That is nothing but types of transformers. There are two types of transformers: step up transformer and step down transformer. First, what do you mean by step up? Step up means increasing the value. That means we give less voltage, it gives us more voltage. If I give 1000 volts, it can give more than 1000 volts based on the number of turns. That I am going to explain. So what is step up transformer? That means if I give less voltage, to the primary. Always whenever I talk about giving the voltage, okay, it is always to the primary. Okay, whenever I give less voltage to primary, it gives us more voltage. That is nothing but step up. Okay, that means increasing the value of voltage. If you want to increase the value of voltage, we have to go for step up. Then step down, if I want to decrease the voltage, okay, I have to go to step down transformer. Why do you want to step down the voltage? That is nothing but, you take an example. For an example, doorbell requires only 5 to 10 volts, 5 to 10 volts, very less voltage. Okay, how much voltage we are getting for our house? That is 220 volts. We are giving 220 volts, but it requires only 5 to 10 volts. That's it, right? So it has to be stepped down, the value has to be decreased. So in those cases we use step down transformer. That is just one example. Next, this is the main key difference. When it comes to the factors, we need to understand everything. Listen, step up. So step up, we are going to talk about step up. That is nothing but here. Okay, so this is step up and this is step down. Step down, step up. Okay, now listen, just these are the symbol we are using just to save the space. Now listen, this is step up. I told how I am telling step up. See the number of turns. See this wire, this complete one wire is called this turn. It is one turn, two. Okay, there are how many turns? Two turns. Here more than two. Which side we have more turns? Secondary side. That means that is step up transformer. If we have more number of turns at the secondary, okay, compared to primary, that means it is step up. More the number of turns, more voltage. Which side we have more number of turns, that side we have more voltage. Keep this in mind. See, in step up transformer, here we have more number of turns. That means here we are going to get more voltage compared to this one. So in step up transformer, N represents number of turns, P represents primary. See, in all the cases, P represents primary, S represents secondary in both the cases. Now E represents EMF. EMF is nothing but voltage, correct? So in N represents number of turns, I we know that is current. So when it comes to step up transformer, why we are using? To increase the value of voltage. So increase the value of voltage means, so voltage at secondary should be more compared to the voltage at primary. Okay, voltage at secondary should be more compared to voltage at primary. Then voltage is directly proportional to number of turns. More the number of turns, more will be the voltage. So in this case also, see here, I told you this is step up transformer, correct? So here the number of turns at secondary is more compared to number of turns at primary. So number of turns at secondary should be greater than number of turns at primary. So voltage, see, important thing is what we want. Step up transformer, more voltage we want. More voltage if we want at secondary, more number of turns should be there at secondary. Keep this in mind. Then these two is exactly opposite to this one. So when it comes to transformers and power transmission, all those things, do you think the temperature remains constant? No, temperature will keep on increasing. That is nothing but it keeps on varying, correct? If the temperature is not constant, Ohm's law will not work. What is Ohm's law? The current is directly proportional to voltage, correct? Only when the temperature remains constant. But when it comes to transformers or power transmission lines, all those cases, the temperature is not constant, then current will be inversely proportional to voltage. Keep this in mind. Now anyhow, so here we got to know, if we want voltage, maximum voltage at secondary, so we will have at secondary we'll have more voltage but less current. But in everything is exactly opposite. If we have, so what is EP? EP means EMF at primary, that is voltage at primary. We will give less voltage, it gives us more voltage. So we are giving less voltage at primary, that means it has more current at primary. This is the important thing you need to know. Then when it comes to TR is nothing but turns ratio, which we have learned previously. Turns ratio, the symbol we use it as small n. So for number of turns we use capital N. Small n represents in transformers, only when it transformers, that is turns ratio. Keep this in mind. For step up transformer, turns ratio is greater than 1. Turns ratio is greater than 1. What is turns ratio? See, I'll write it here. ES by EP is equal to NS by MP is equal to IP by IS, correct? So This is the turns ratio formula. You take any one in any one of these, ES by EP or NS by NP or IP by IS, you take any one, the value should be greater than 1. I'll show you how. See, for step up transformer, what I told, the turns ratio is always greater than 1. I'm going to show you how it is. See, in this case, you will talk about only voltage now. So we know in step up transformer, the secondary voltage is greater than primary voltage, correct? If the value of numerator is greater than the denominator, we will definitely get more than 1. Assume we are getting 2000 volts and we are giving input voltage is 1000 volts. 2000 divided by 1000, 2 by 1, that is nothing but 2. So it is more than 1. Now we'll talk about number of turns. We know number more, if we want more voltage, more number of turns should be there. So here secondary number of turns are greater than compared to the primary, correct? So NS is greater than NP, so numerator is greater than denominator, obviously will get more than 1. Then IP by IS, this is very much important. When it comes to current, everything is exactly opposite. So IP by IS, I told you for step up transformer, input current is greater than output current. So greater numerator value, less denominator value, obviously will get greater than 1. So for step up transformer, keep this in mind, turns ratio is more than 1. All these things you have to make a note, then only you can remember these things for a longer period of time. Now we'll go for the final topic about step up transformer. Thicker wire. See, which side is thicker, that is very much important. Based on this one, in 2024, one question was asked for 1 mark. Identify the type of transformer, in which side of the transformer the wires are thicker. When it comes to thickness of the wire, it depends upon current. More the current, thickness of the wire should be more. If thickness of the wire is more, it can hold more current, correct? So thickness of the wire is directly related to current, directly proportional to current. Which side current value is more, that side the wire will be thicker. In any one of the transformers, we need to identify which side we have more current. Okay, so here we have more current, IP. So when it comes to step up transformer, thickness of the wire, primary side thickness of the wire is more. Keep this in mind. For a step up transformer, primary side thickness of the wire thickness is more. Instead of by hearting this, how to understand is more the current, which side we have more current, that side we have thicker wire. So current at primary is more, correct? So thickness of the primary wire, so this is the primary, right? So we are talking about step up. So this is a step up transformer. Here primary side we have more current, correct, according to this one. So that means primary side wires have more thickness compared to secondary side. Now we'll jump into step down. So all these things are very much important. Now whatever we have learned, exactly opposite, everything is opposite. That's why don't learn both the things. Learn any one. Step up transformer, everything will be opposite to step down transformer. We are going to learn here. Now listen, step down. What do you mean by step down? We are giving more voltage, okay, it will give us less voltage. We are giving more voltage, it will give us less voltage. So this is very much important about step down. Okay, now here, so step down means decreasing the voltage, correct? So this is the example for step down. Here see, the stepping down means decreasing the voltage. If we want less voltage, less number of turns should be there on secondary. Okay, so see here, less number of turns, that means less voltage at secondary, more number of turns at primary, so more voltage will be there at primary. So when it comes to step down, what we want, less voltage, so we have to give more voltage. So voltage at primary will be greater than the secondary. We know voltage is directly proportional to number of turns, and it is exactly opposite. Why? Because more the, see, where we have less voltage, there we have more current, correct? So it is inversely proportional. At secondary we have less voltage, so at secondary we have more current. Then turns ratio is always less than 1 when it comes to step down transformer. How we got to know turns ratio is greater than 1? Using this formula, correct? The same method you apply here. Turns ratio you will always get less than 1 in step down transformer. Then thicker wire, which side of the wires are thicker? So whether it is primary or secondary, which side we have more current? See, thickness of the wire is directly related to current, correct? So and I'll teach you one more way to identify the thickness of the wire. Now thickness of the wire is directly proportional to current. More the way which side we have more current, that side we have thicker wire. So in these two cases, okay, when it comes to step down, which side, primary side or secondary side we have more current? Secondary side, right? So thickness of secondary side, thicker wires we have. So how to identify thickness of the wire in a different way? See, this is an alternative way to find the thickness of the wire, but if you have understood the first one, you can go for the first one, just an alternative way, different way. Which side we have less voltage, that side we have more thickness. Okay, when we will go to step up transformer, which side we have less voltage? Primary side, correct? So that side we have more thickness. See, primary side. Apply the same method. Okay, step down, which side we have less voltage? Secondary side. So secondary side thickness is greater. But thickness is directly proportional current. Okay, more the thickness. Okay, why? They'll ask one more question. Why the thickness of the wire should be greater at primary in step down, step up transformer? The reason is more the thickness, less the resistance, so more current it can withdraw. Okay, why the wires has to be thicker? That means more the thickness, less the resistance, so more current can flow. This is the reason why we have to use thicker wires. So these are some basics, okay, complete basics about transformers. Now we'll talk about losses in transformers. So there are three types of losses. First one, copper loss. Copper loss, it is not a loss of copper, it is something different. See, when it comes to copper loss, the loss of energy in the form of heat. If the energy is lost in the form of heat, that is called as copper loss. Then how to minimize it? So in all the three different losses, how to minimize this is very much important. Definition is not important. Only for the copper loss, definition is given. So how to minimize the copper loss? By using a thicker wires in the transformers. Thicker wires in the transformers. As the wires are thicker, the resistance reduces. If we know resistance and temperature both are directly proportional. If resistance reduces, temperature also reduces, so we can avoid the loss of energy in the form of heat. So how to minimize it? By using the thicker wires. Next, we talk about eddy current loss. Eddy current loss. So eddy current loss. So definition is not important here because that is not given in the textbook and it is not also in the syllabus. How to minimize eddy current loss? This is one loss in transformers. So how to minimize the eddy current loss? By laminating the core. By laminating the core. Remember all these values, the points. That is very much important. The third one is hysteresis loss. Hysteresis loss. So hysteresis loss can be minimized by using the soft iron as a core. If we use soft iron as a core, hysteresis loss can be minimized. See, the definition of eddy current loss and hysteresis loss is not there in the syllabus. You are going to learn in higher classes like first PU or second PU. Now present copper loss definition is there, and for all the three losses we have to show how to minimize all these losses. Now we'll talk about uses of transformers. There are two types of transformers. First we'll talk about uses of step up transformer. Step up transformer is used in power generating station. In power generating station we have to generate high voltage, right? So in power generating station step up is used. Then in olden days television picture tube. In olden days TVs we used to have there is a part called picture tube that requires high voltage. There we used to have step up transformers. Then the X-ray machines, MRI machines, all those machines, X-ray and MRI requires high voltages. These are the uses of step up. So now we'll talk about step down. Step down is used in mobile phones. That means mobile phones does not require high voltage. They require very less voltage. Okay, very less voltage. But how much we are getting? Okay, we are getting for house 220 volts. But we don't require that much voltage for mobile, computers, and electric bells and nighttime bulbs, night light. Okay, night light bulbs, the small watt bulbs. In all these things we use step down transformers, and Power substations. In power substations, we use step-down transformers. What is power generating station and power substation? This is what we have learnt in household circuits. Now, these are the uses of step-up and step-down transformers. If you have understood everything about step-up and step-down transformer, the differences will be very easy for you to understand. Listen, step-up transformer. Why we use step-up transformer? To increase the voltage. Step down, it is exactly opposite, to decrease the given voltage. Next, in step up transformer, see, we know, okay, ns is greater than np. Ns is greater than np. See, to increase the voltage, number of turns at secondary, okay, should be greater than number of turns at primary. Then this is exactly opposite. np is greater than ns. Next, we know in step up transformer, IP is greater than IS, because we know in step up transformer voltage at secondary is more, but voltage and current are inversely proportional, correct? If secondary, if voltage is more, current will be less. That means at primary current is more. Then this is exactly opposite. Okay, next, you can go for thickness of the wire. We know thickness of the wire completely depends upon the current. Okay, which side we have more current? At step up, primary side the current is more. That means the thickness of wire is more at primary. Here in step down it is exactly opposite. Then you can write one of the uses. Step up transformer, where we are using, there are many uses we have learned, right? You can write any one. Step down also you can write any one use of the step down transformers. Now we have understood the complete informations about electromagnetic inductions, Lenz's law, Faraday's law, transformers and AC generator. All these things are very much important. When it comes to electromagnetism, I am again saying, within 1 minute you can get 3 to 4 marks if you have the complete knowledge. So try to solve all the questions, okay? So first learn all the questions from the theory solutions, okay? That video is available in the description box. And after theory we have some numericals, learn that also. Everything is very much important. So I believe you have understood of the complete concept. So after all these things, concept, theory solution, numericals, we are going to solve each and every questions from previous year paper, that too chapter wise. From electromagnetism chapter, what are the questions they have asked, only from that then you can get the complete knowledge. Then logical questions and logical and application questions about electromagnetism and MCQs about electromagnetism. All these things are created as playlists. All those videos are available in the description box. Watch it, learn it, get 80 on 80 without touching the textbook. Thank you.